In this short video, we're going to look at three things. We're going to look at the burning of magnesium, whether in air or in oxygen. We'll take a look at the burning of sulfur in oxygen, and we will finish up with the preparation of oxygen from hydrogen peroxide solution. Most people have seen magnesium burn in air. It burns giving off a bright white light that can be damaging to the eyes and should not be looked at directly. The product of burning, the product of combustion, is the white powder, the residue of magnesium oxide. If we remember the air is only 21% oxygen, what would happen if we replaced that with 100% oxygen? We'd increase the concentration of oxygen gas. And we can do that using a gas jar and a burning spoon or a deflagrating spoon. Here we've wrapped a piece of magnesium ribbon around the base of the deflagrating spoon, adjusted it to the right height, and we're setting fire to the magnesium ribbon in air and then plunging it into the gas jar of oxygen. You should notice it burns with an even brighter light. Now sadly, our burning magnesium touched the side of the gas jar and reacted with the silica in the glass, in the silicon dioxide, which forms part of the glass, and has had a second reaction producing a black precipitate and resulted in us breaking the gas jar. This is a reaction where a metallic element reacts with a non-metallic element, the oxygen, to form a compound. In terms of electrons, the two outer electrons of the magnesium are transferred to the outer shell of the oxygen atom, forming the O2 minus ion. So this is an electron transfer. The attraction between the negatively charged ion and the positively charged magnesium ion leads to ionic bonding when you consider the many billions upon billions of particles that would actually take place in the reaction. In the reaction where we burn sulfur in oxygen, we get a rather pungent, rather smelly, white misty gas called sulfur dioxide. Sulfur dioxide gas is acidic and it's not very good for those who suffer from asthma or other breathing troubles. As before, we set fire to the sulfur in air, and you should be able to see it starting to burn with a blue flame, a characteristic blue flame of burning sulfur. And when we plunge it into the oxygen in the gas jar, it burns much more profusely and the blue flame is more evident, as is the white misty gas sulfur dioxide. This time we're reacting a non-metal with a non-metal. This results in a molecule containing covalent bonding, and it's typical of non-metal oxides to be acidic. To prepare oxygen gas, one method is to break up hydrogen peroxide solution. Hydrogen peroxide is H2O2, so think of it as a water molecule with an extra oxygen chemically attached. And we can break this apart using a catalyst. Now there are several catalysts that can be used. The one I'm using here is the black powder manganese 4 oxide or manganese dioxide. So we're dribbling some hydrogen peroxide solution onto the catalyst and taking the gas that's formed straight out into a trough of water in which we've got some tubes or measuring cylinders filled with water to start with, and we're collecting the gas by the downward displacement of water. For those of you that understand about oxidation numbers, this is an interesting reaction. The oxidation number of oxygen in hydrogen peroxide is -1, and oxygen appears in two different products. It appears in the oxygen gas, being elemental. It has an oxidation number of 0. It also appears in water, where it has an oxidation number of -2. So in the one case, the oxidation number increases. In the second, it decreases. Where such a reaction occurs, we refer to this as a disproportionation reaction. Don't get confused with the oxygen in the manganese 4 oxide. That's a catalyst and therefore remains recoverable at the end. The oxygen in MnO2 does not form part of the oxidation products or the reduction products.